Start.
Yep, let's go ahead.
Good morning to all of you, and I warmly welcome Professor Sarabjit Banerjee again on the day 4 of the Indo-US webinar and lecture series. For the lecture series, it is the second day, and we have enjoyed the first lecture from Professor Mao, and it is our second and last lecture by Professor Sarabjit Banerjee on a very hot topic of lithium-ion batteries. As we have observed that lot of questions from the participants who were asked during last 1 or 2 days from Professor Banerjee. So this lecture will be very interesting and the participant will find very interesting for them. And the title of this lecture is Designing Electrode Architecture Across Length Scales, Some Lessons Learned from Lithium-Ion Chemistries. So this is a very hot and interesting topic. So I request Professor Sarabjit Banerjee to please start his special lecture.
Thank you very much, Tokir. It's a great privilege to be here, and I think very complimentary set of talks. Dr. Mao spoke earlier this morning on hydrogen storage, so it is my sort of privilege to talk about not storing hydrogens, but storing electrons, right, in the form of lithium-ion batteries. And so this is a part of a two-part lecture. I'm going to talk about lithium-ion batteries today, and then about beyond lithium, the future beyond lithium-ion batteries for energy storage on day 6, right? So day after tomorrow. So I just want to thank my group that has worked on many aspects of this work, starting with Luisa Whitaker-Brooks, Chris Petrich, and Jesus Velazquez, and this work was carried on by Greg Horrocks, Luis de Jesus, and then Justin Andrews, David Santos, most recently, Rachel Davidson, Wasif Zahir. And most of the work I'm going to tell you about today is in collaboration with a number of folks, David Prendergast, the Lawrence Berkeley National Lab, Louis Piper at SUNY Binghamton, the group of Professor Baishang Xu at TU Darmstadt, and these are the main collaborators for this set of results I'm going to be telling you about. So as I spoke yesterday, we are in the midst of an unprecedented energy transition, right? So our demands for energy are dramatically increasing, and along that comes a lot of challenges. Where do we find this energy to meet these massive needs, and how do we do this while preserving our climate, right? We're also, like I talked about yesterday, we're not only in the midst of this big energy transition, we're also facing this huge challenge, this generational challenge of what to do about this increasing carbon content, our carbon emissions. And it looks like we're even going to have to do some negative emissions. That means that it's not going to be sufficient to do zero emissions. We're even going to have to take some CO2 out of the air, right? So you know, as I talked about, we're in the midst of this transition. It's not going fast enough. There is a need to accelerate the transition, the energy transition to renewable sources of energy. So as you can see, about 83% in 2018 was non-renewable still. What is starting to happen though worldwide, we're seeing a sharp decrease in the use of coal. We're seeing solar go up and wind go up, and these are probably the two sort of biggest vectors of change, and this is going to be great for our climate. But as I have talked about in my first lecture as well, you know, wind turbines are really enjoying an amazing boom. Our U.S. wind capacity in 10 years has increased by 431%. Similarly, solar energy, like I talked about yesterday, there's been a really sharp drop in the cost of solar panels, and that has driven massive adoption along with governmental incentives. And so, you know, we've got 12 million homes powered in the U.S. now with solar, and that capacity is rapidly increasing. And I talked about the concepts of levelized cost of electricity, levelized avoided cost of electricity, and on that equation, solar is a clear winner, and it's something that is therefore advancing across the world, right? But solar and wind bring with it two unique, lots of unique problems. When we talk about the overall stability of the grid, you need power when you need power, and if the sun is not shining, like it's the middle of the night here, where do you get power if you need it, right? Or if the wind is not blowing, or if there's 7 days of continuous rain, where do you get this? So the capacity factor. So how often a plant is running at maximum power? This is quite low for solar. This is a problem. So 24.5%. Wind is slightly higher, 34.8%. But this essentially means that we're going to have to do something to store this energy, right? So this is really one of the big driving forces. One of the things I want to introduce, there's a lot of concern now about the idea of curtailment. So what does that mean? And this is also very true in India, not just in the US, but India and California have very similar profiles. So the point of this curve is this duck-shaped curve is the fact that, here's solar in yellow, wind in blue, right? And then our load is in here, and you end up having to curtail the amount of renewable energy produced because in the absence of storage, you have nothing to do with it, right? So essentially, you generate a bunch of electricity. If there's no demand at that given time, you just have to throw it away, or you basically just stop producing power, right? So essentially, we are throwing away a lot of power. This in California, it's been estimated that about 1/3 of the capacity of renewable energy is wasted because there's not enough storage, right? So essentially, you're producing power, but if you don't need it, there's no way to do anything with it, so you just stop producing in the meantime. This is important for grid stability. So to limit curtailment, the number one thing that has to happen is there has to be increased participation by energy storage resources. Okay, so that is key to better utilization of solar energy or wind energy. It's also important. There's other solutions to this. Another part of the solution is to have, for instance, a much bigger distribution network. So if you're producing solar in one area and there's no demand for it, can you take that energy and move it far down the grid to some other region, right? Or another very interesting idea, this is already being done in Japan very effectively. Can you use electric vehicles as part of this whole, as essentially large batteries? So essentially, can you, when there's a time of excess power, instead of shutting off the renewable energy power, can you plug in cars and power them up while there's excess power available, right? And then the cars are all charged up, ready to go, right? So lots of need for batteries to address this idea of renewable curtailment. And so where do we go here? So there's two big needs for energy storage. One is, it's important to decouple electricity generation from the load or electricity user or the demand, and this will make it easier to regulate supply and demand, right? So this is really, really important. One of the things that batteries are already doing very effectively is the idea of load leveling or peak shaving. So if you've got only 1 hour of very high demand for electricity, you could produce 80% of it and then provide 20% with an external battery, right? So that way you don't have to have power generation capacity at 100% all the time when you're only going to need to supply that power for 1 hour, right? So then also the idea is it makes the whole thing more secure because we can have distributed storage grids, microgrids, which will greatly improve our grid security and allow this to happen. So my very first lecture I gave on hydrogen, and I'm going to talk today about lithium-ion batteries, and then we'll think about beyond lithium chemistries in my next lecture, right? So considering possibilities for storage, lithium-ion batteries are not the only one. There's plenty of options out there. This is a good plot from RMIT that I borrowed here. how much can you store, how fast can you get it back on the vertical axis, right? So you've got technologies like flywheels, so where you cannot store sort of physical storage mechanisms, you cannot store very much, but you can get it back very quickly, right? On the other extreme, you've got something like methane, so electricity, the power generation, or what I talked about on day one was hydrogen. Dr. Tokirama does a lot of work here. How do you take power, convert it into gas, hydrogen gas, right, and store it? And again, you could potentially store a huge amount of energy in the form of hydrogen gas. Relatively slow getting that energy back because you have to essentially use a fuel cell to burn it, right? And then you have to address storage like Dr. Mao described in the first lecture this morning, right? Pumped hydropower is actually an excellent solution that's very popular, but of course you need to have large bodies of water and large tanks, and it has to depend on the geography, and you have to move water up. Essentially very simple, where you're just moving water up, and then when you need to, need the electricity, you let the water come down, right? Batteries are increasingly going in every direction in terms of increased faster discharge times, in terms of higher and higher capacities. Some of the redox flow battery technologies are now well into the gigawatts regime, and so these gigafactories are coming online. So there's a lot of opportunities here for batteries. So since the theme of our seminar is functional materials for energy, I'm going to focus primarily on these material storage technologies, right? So we talked about hydrogen. Now I'm going to talk about batteries. So these are, but this is not to say that these are not viable technologies. Pumped hydro storage is currently the dominant technology for grid level storage, but mostly, again, a simple pumping mechanism, more of a physical mechanism, right? This is another way of looking at this, and I like this breakdown here. So everything on this end. So supercapacitors, there was a question about supercapacitors last time, mostly for power quality, right? So if you've got slight fluctuations in the grid, you can address that, and you can get uninterrupted power supply with these sorts of energy storage technologies. And then you've got the idea of load shifting or peak shaving that you can do with a lot of these batteries. And if you're really doing long-term bulk power management, then generally speaking, we're not talking about too many battery technologies. There's redox flow batteries are extending into this regime, but the dominant technology is pumped hydro or compressed air energy storage. But again, very strong play, perhaps not by lithium ion, but mostly by vanadium redox flow batteries in this regime. Okay. So the two massive drivers for new battery development, one is electromobility and the other is grid level storage. So electric vehicles and then grid level storage, and they both have different considerations. So I like this quote. There's a lot of energy. As Dr. Tokirama said, this is a very hot topic, right? The battery electric vehicle is showing signs of life, but and this is a quote in Nature, but it's important to note the date, 1934. Right? So from 1934, we have been talking about electric vehicles, but still a long ways to go, right? So we stopped talking about it. We started talking about it again. We stopped talking about it. So this technology has seen a lot of ups and downs, and science has not done enough to solve the problem. So, so still, I think we're making amazing progress right now, but there's still lots of work to do. So in terms of actual performance that a customer cares about, you care about energy density, how much energy can you actually store, power density, right? So how quickly can you get this out? Safety has become a huge consideration, oftentimes the number one consideration. We are all carrying with us lithium-ion batteries, right? If you've got a cell phone, if you've got a laptop, you've got maybe 2 lithium-ion batteries you might be carrying, have in the room with you right now, right? But and you've all seen videos on YouTube. Hopefully, you haven't seen it in real life of cell phones catching fire, or YouTube or laptops catching fire. Not something good at all. But as we build bigger batteries, because we have to build much bigger batteries for cars and even bigger batteries for grid level storage, safety becomes obviously a much bigger issue, right? So as the magnitude of the batteries increase, we have to really, really worry about, what does this mean for safety? And lithium has some intrinsic challenges, which I'm going to get to in a second. Depending on the application, you might care about portability or mobility, and then the next thing is capacity retention. How many cycles can you get out of it, right? Do you get 1,000 cycles? Do you get 10,000 cycles out of your battery? And it depends again on what sort of application you have in mind. So lots of technologies out there, starting from non-rechargeable batteries. That's of course the old technology where batteries first started. Then you've got lead acid batteries and lithium ion and these massive flow batteries. And then of course hydrogen in some cases is a very viable solution, right? So I'm going to show this curve. It's a sort of an interesting view of the history of batteries, starting from lead acid, right? If you take a look at the energy density here, and then the volumetric energy density on the vertical axis, and then you go from lead acid in 1859 to nickel metal hydride, and finally to nickel cadmium, then nickel metal hydride, and then finally the lithium ion in 1991, first commercialization by Sony, right? And if you take a look at this is an interesting contrast for energy density of batteries over the last 150 years. It's a relatively small number, and as far as technology grows, we've only been managed to get a 4x increase in 150 years. And I on the same plot is plotted Moore's law. Many of you have heard about Moore's law, which is basically talks about the capacity of transistors or capacity of electronic circuits, and basically says that we have twice the number of transistors in a chip every 18 months. So we've got this massive increase in computational power. You're carrying in your hands extremely powerful computers inside your cell phones that people wouldn't have imagined 30, 40 years ago. And again, Dr. Didi Sarma gave a very beautiful talk showing you some pictures of how dramatic this progress has been. There's been a 50 million X increase in the number of transistors, megabits per square inch in time. There's been a 45,000 X increase in number of junctions per chip in 30 years. But then if you think about batteries, much slower progress. So this is a difficult problem, and it's going to need a lot more work. And I think only in the last decade have we really started to see a very concerted push. And the reason for the concerted push is very clear. The full promise, realizing the full promise of renewable energy is now relying very extensively on the shoulders of being able to make advances in battery technology. Okay, so the idea of a lithium-ion battery is quite straightforward. From the perspective of thermodynamics, when you are actually using the battery, right, the thermodynamically downhill reaction is the lithium ion moving from the anode, which is the graphite, into some sort of transition metal oxide cathode, right? And at the transition metal oxide cathode, you have a redox reaction happen, specifically a reduction reaction, right? And that's exactly how we understand this from your first year chemistry courses. Reduction reaction happens at the cathode. So the ions move past the separator into this cathode, and then meanwhile the electrons are also moving right through an external load into the cathode, and so by convention we say that the current moves in the other directions. This is the act of using the battery. So if I have a cell phone and I'm using it right now, this is what we're doing, and it's a thermodynamically downhill reaction, right? And then the thermodynamically uphill reaction, the disfavored reaction, is pulling the lithium ions out from the cathode and then putting it back inside the anode, which is graphite, right, across the separator one more time. And again, now the electrons are moving from the cathode into the anode, and then current is moving again in the opposite direction. So this is what happens when you plug it in. This is the charging process, right? And then this here, right here, is the discharging process. And so if you think about this, this is a chemical reaction. These are the equations for the electrochemical reactions that are written at the bottom. And you know, for a battery to work over as many cycles as it does, this is a chemical reaction that has to occur with a very, very, very high yield, right? So if those of you that are students, you go in the lab and as part of your practicals, you're asked to do an experiment and report a yield. And if you get a yield of maybe 89%, you're very happy with yourself. But you think about this, 89% in one cycle times 89% in your second cycle times 89% in the third cycle. Very, very soon, your capacity has decreased dramatically, right? So for this reaction to work, you have to have very high yield of this reaction, right? Almost 99.99% every step for us to get enough cycles out of this, right? So this is a very important thing. So, and this is a very important distinction, and it's a very important distinction from the perspective of rechargeable lithium-ion batteries, right? And so if you take a look at this, lithium-ion batteries, it's just had such a dramatic rise, you know, from the first invention by Stan Whittingham is the first person who came up with the idea of lithium-ion batteries, and he proposed a titanium sulfide cathode, and then John Goodenough proposed some oxide cathodes, and then still combining it with lithium metal, and then Akira Yoshina came up with the idea of a graphite anode. So across 3 countries, and then Sony first commercialized it in 1991, and then you've had this meteoric rise, and it's a technology that has changed even in our lifetimes, right? The very face of urban society, right? So laptops have become possible because we have these batteries. We've had, you know, the first, of course, technology that came out that was powered by this was the Sony Walkman, right? The idea of mobile music became a reality. Ultimately, cell phones, all powered by lithium-ion batteries. So if you take a look at this, for the last 10 years, the dominant category has been consumer electronics. Lithium-ion completely dominates this category. It's in green here. But as you can see already by 2020, 2021, the biggest player now is no longer consumer electronics, but passenger electric vehicles. Even though, as I showed you in my previous lecture, passenger electric vehicles are about 3% of current vehicles on the road or produced per year, not even on the road. It's lower percentage there. Okay, already more lithium ion batteries are being produced for electric vehicles than for consumer electronics. Okay, and so commercial EVs a little bit here, and you can see there's a very rapid meteoric rise in gigawatt hours, and mostly driven by passenger electric vehicles, commercial electric vehicles, and things like and a little bit like stationary storage. Still lots and lots of challenges to be overcome in stationary storage. There's big challenges we'll talk about, especially for long-term energy, but certainly electromobility is dominating it. And these are some pictures with Stan Whittingham. I've been fortunate to have had him as a mentor in many respects, and it's been just great to have his advice and his guidance on many of the things we do. And this is Dr. Prashant Kamath from ACS Energy Letters, who's also a great scientist. So we've been so when you think about the whole energy storage problem, the invention of the lithium-ion battery was really pivotal to the growth of consumer electronics and these emerging technologies. But now, as we move towards problems like electromobility and grid-level storage, the need to safely store energy with high energy densities and such has really increased, and we're dealing with a lot of challenges, all the way from deep technology challenges that have to do with kinetics and thermodynamics to challenges in mechanics. This is something that I think is also an incredibly hot field right now, is the coupling of electrochemistry with solid mechanics. Okay, and there's a lot of new science here and a need for some, I would say, non-traditional collaborations between chemists on the one hand and mechanical engineers on the other hand to solve some of these challenges, because mechanics plays a big role in degradation of batteries. I'm going to show you some reasons why. And then in terms of sustainability, materials criticality has become a huge problem. Also, manufacturing science. So there's a lot of deep science here that has to be done, right? So and like I said, 1/3. This is some work that David Santos and my group has been doing, not just looking at the material development side, but the more getting a more global view of what is going on in the battery markets. And so again, 1/3 of all renewable energy, approximately, especially in areas with high density, are getting wasted because we don't have energy storage. So all our massive investments in solar, our massive investments in wind technologies will not come to fruition and will in fact be wasted if we do not have good storage technologies to accompany it, right? And so understanding how this works, again, it's a challenge across multiple scales, starting from atomistic dimensions to single particles to mesoscale phenomena and to the levels of full stacks of cells, right? And this is it requires understanding controlling flows of charge, flows of mass, flows of energy from the level of atoms to systems, and then controlling lots of different time scales. There's some real large challenges here for us to work with, right? So the backbone of electrochemical energy storage are transition metal oxides, right? The cathode, I'm going to mostly focus on this today. Tomorrow or in 2 days, I'll talk a little bit more about anodes, but I'm just going to sort of mention this today. But the dominant technologies here are lithium cobalt oxide or lithium ion phosphate. This is a view of how sort of some materials considerations, right? So on the one hand, you care about potential. This is something that you learn about in your electrochemical series, right? So on the your lowest potential here is lithium metal, and you've got graphite here, right? And you've got these transition metal oxides at higher potentials. And so essentially your cell potential is the potential of the half cell potential of the cathode minus half cell potential of the anode, right? So if you want to have a larger voltage for your battery, you want to pick something as high as possible as your cathode and as low as possible as your anode. So the lowest anode, sort of the possible choice here, is lithium metal, right? So why don't we use lithium metal? This has mostly been a problem with safety, right? So the lithium forms dendrites. And again, there's been many companies that have tried and many academic labs that have tried to use lithium metal, and they've tried to get it to cycle into plate in the form of homogeneous uniform thin films. And it's been incredibly difficult because some fraction of times it does not plate as thin films. It forms dendrites, and those dendrites will essentially short circuit the battery and essentially get this thermal runaway going, which essentially results in all these large battery fires you see, or just the battery getting completely dying, right? So a big dream for the entire field, something everybody's working on, or a lot of folks are working on, is to be able to use lithium metal anodes safely, reliably, and at full scale at large batteries. And this is yet an unsolved problem. There's lots of claims in the industry. Many of those claims have been proven to be not entirely true. This turn is a huge problem. How do we get to go from graphite to lithium metal? So this is something that a lot of folks are working on. So trying to mitigate the propensity for dendrites, and so moving away from graphite-based anodes to lithium metal anodes. And then on the cathode side, lots of progress again in these pushing the voltage. These manganese oxides with different dopants are high voltage cathodes, but then sometimes, as you can see here, their capacity is low. So it's not just the vertical axis that is important, which gives you the voltage, but also your horizontal axis, which gives you the capacity, right? So as compared to these high voltage oxides, these vanadium oxides here are high capacity cathodes, right? And so I'm going to mostly focus on this. This is where we've done most of our work. Ideally, but this kind of tells you what you're looking for. We would like to move. We would like to move in this direction, right? Get cathodes to be higher voltage, higher capacity, and we would like to use our our low voltage and high capacity anodes to the extent possible. So that's the dream. And again, the theoretical capacity is the number of electrons you transfer times Faraday's constant by 3.6 times the molecular weight, right? And again, the delta G, the Gibbs free energy, is related to the potential difference between the cathode and the anode, right? So that tells you sort of how the thermodynamics is directly related to the cell potential. A very big push right now is to look at a slightly different configuration. So a conventional lithium-ion battery has a porous cathode, like we talked about, and a porous anode, and there's a separator in between that usually has some sort of a liquid electrolyte that's soaked with it, and you've got current collectors, and you can kind of, you've got two different current collectors, and you sort of have them all attached here, and I'll have them all attached. You can build a full stack, and you might even have a cooling system. So a real major push that is going on is to build these all solid state batteries, and build all solid state batteries with lithium metal anodes and dense solid electrolytes, where you can somehow mitigate lithium dendrite formation, and then to have a dense cathode composite. So very high capacity on the anode side, high capacity on the cathode side, and then a fully solid electrolyte that somehow prevents this whole this lithium from coming through. And they would again be connected here. And if you kind of got it to work in the right manner, you wouldn't even need a cooling system. So here's a graphic that I borrowed from Dr. Piero Canepa. Lots of challenges. The big challenge that has to be solved is to use lithium anodes. Is still incredibly difficult, because even though these are solid electrolyte, they still show lots of dendrite formation or mossy lithium formation, at grain boundaries. The other important challenge, big challenge in a solid state battery, lots of things happening, lots of electrochemical reactions that take place at these interfaces between the cathode and the solid electrolyte, the anode and the solid electrolyte. There is a need to maintain physical contact as these things expand and contract with charging and discharging. Okay, so this is a big problem, and typically done by having a large stack pressure that keeps these holds these in place. But this is a major issue because there's very large volume changes going on during cycling, and it's important to keep physical contact. The other thing, of course, is what is the nature of these interfaces, for instance, between a cathode and a solid state electrolyte, and how well are these interfaces preserved, or how do they dynamically evolve as a function of time, right? So in terms of the cathode, I'm going to dive a little bit deeper into this, and a lot of the ideas are translatable to the anode as well. I'm going to mostly focus on one electrode, but you can sort of think about similar things on the other side as well. And there is some transferability to also except you're not storing ions in there, but to the solid electrolyte as well, right? So in general, this again comes down to a play of thermodynamics and kinetics. You need to have a large delta G between intercalated and deintercalated phases. So for example, between lithium cobalt oxide and cobalt oxide, right? And it should be large because why? Because delta G is equal to negative NFE, right? So if delta G is small, the actual cell potential that you get out of it is going to be small. So that you're not going to get very much out of a voltage out of that, right? So delta G has to be relatively large, but it's not so large that it's, the reaction is essentially, impossible or irreversible, right? So those sorts of batteries do exist. We call them primary batteries, right? So they're non-rechargeable because the reaction sort of only goes in one way. It's impossible to go back. Now, ideally, you want to have lithium ions entering the solid, and this process, this intercalation reaction or insertion reaction that's reversible, should bring about a relatively small change in lattice volume, right? Again, this is important because if you imagine this active element, if there's very large changes happening in lattice volume, that will result in lots of mechanical instability, and especially this is true for these all-solid-state batteries, but it's generally also true, and that is a leading cause. I talked about the coupling with mechanics. These large volume changes will oftentimes result in substantial failure. A cathode material should have a high abundance of interstitial sites, so lots of areas to store the ions, because the ions have to go somewhere, right? And this is a key difference from a supercapacitor, right? So in a supercapacitor, most of the energy storage or all of the energy storage is happening at the surfaces, but in a battery, you actually have redox processes that are going on inside the bulk of the material, right? And it's happening inside the bulk of the material because the ions are able to penetrate. And by doing so, they're accessing these transition metal sites and doing reduction or oxidation, depending on whether you're discharging or charging the battery. And you're actually accessing the interior of the particle. And this is, again, a very key difference from a supercapacitor, where every reaction is sort of happening on a surface. You work really hard to increase the surfaces. But here, you really have to, you're being able to utilize transition metals located inside. And why transition metals? Because they've got multiple redox centers. So that's the second point. You've got to have accessible redox centers that you can reduce. And so you're essentially doing energy storage through the form of redox reactions at transition metals, right? So for instance, if you're doing manganese chemistry, you're cycling through the different oxidation states of manganese, right? So thermodynamics is necessary but not sufficient. You also need kinetics, right? So the ions, like I talked about, they have to enter here and penetrate through the bulk of the material, right? So we need to have low site-to-site diffusion barriers. The ions have to be able to move through the lattice. So if they get stuck, if the barriers for them to move from one side to another is large, then this becomes a major challenge. And so if you ever wonder, why do we have lithium-ion batteries in the market and not aluminum-ion? This is the question. This is the answer, right? Because lithium ions, lithium being the smallest metal, one of the answers is that it relatively easily moves through this lattice, right? This is the reason. And I'm going to talk in 2 days about beyond lithium ion chemistries, and most of them are not commercial at this point. And the big challenge here is, how do we diffuse ions through a lattice in the same way that we are able to diffuse lithium ions, right? And then the next problem we have to solve, lots of interfaces, either solution phase interfaces or solid state interfaces in the case of all solid state batteries. But for example, an interface here between the electrolyte and the cathode, or electrolyte and the anode. And at that interface, right, the lithium ion, as long as it's in the electrolyte, is coordinated by some sort of counter ion, right? There's some sort of counter ion with it. It's got to leave that behind and enter inside the solid. So that's these desolvation reactions that are required. And then the other thing I talked about, I sort of briefly alluded to before. So you've got this whole series of intercalation reactions happening, right? So the intercalation reactions require that these sort of diffusion of ions through the lattice does not have a large barrier, so the ions can readily move through the inside of the lattice. They also require very easy solvation at the surfaces, right? But these two reactions have to be easier than parasitic reactions. So a parasitic reaction For instance, in the case of this system, could be the lithium reacting with oxygen to form lithium oxide and some sort of cobalt suboxide, right? So this is a problem because once that reaction happens, it's almost it's going to be very difficult to sort of get that to reverse, and then you've lost that capacity, right? Because you're not going to get that cobalt back. It's going to stay in this in its reduced form, and then you're sort of stuck. So this is a very important point, that these insertion reactions must be very strongly favored over parasitic reactions. So I'm going to start with one cathode we particularly like, which is alpha V2O5. So Stan Whittingham, in his some very seminal work back in the 70s, proposed using this as a cathode for lithium-ion batteries. Why? Because it makes all sorts of sense. You've got lots of open sites here. You've got vanadium here, which you can reduce from vanadium 5+ to 4+ to 3+, and even lower if need be. And so this seems to make a lot of sense. But then it turned out not to be so great. Why is it not so great? So on the one hand, it's got a very high theoretical capacity, about 440 milliamp hour per gram. It's got multiple possible accessible redox states. It's relatively high abundance of interstitial sites. The undesirable aspect of this is that it undergoes a series of phase transformations. As lithium ions go in, the lattice expands, the lattice distorts, and so you go from this structure here to this epsilon structure here, and ultimately to this delta structure, and then a gamma structure. And at this point, the sheets are no longer straight; they become extensively distorted, and then and at this point, generally it's irreversible, and this causes a lot of challenges. So essentially, what's happening is that the introduction of lithium ions is forcing some pretty large changes in structure, right? And that's really not ideal for a whole lot of reasons. So about a decade ago, we started thinking about what exactly is can we dive down into the chemistry of the system. And so if you actually look at the lithium ions and where they sit inside the lattice, it turns out there is a pretty large change in the local coordination environment as the ion moves through the lattice. So you go from being 8 coordinated to being 3 coordinated in the transition state to being 8 coordinated again. So what this means is that there's a lot of bonds being broken, new bonds being made, and then bonds being broken again, but a big change in coordination as the ion moves through, and therefore the barriers tends to be pretty high, about on the other 0.22 electron volts for lithium, not that high, but relatively high. And then, as you can see for other ions, this becomes a huge challenge. And I'm going to focus on other ions mostly in my next lecture. Today we'll talk mostly about lithium. So again, we talked about this in a battery, during the discharging of a battery, right? So the ions are moving into the cathode, right? Electrons are also moving in now from the current collector, right? So now the challenge with the electrons moving in, ionic diffusion is problematic. Comes from some fundamental ideas of crystal field splitting, like you would have studied in again, your basic inorganic chemistry class, right? So V2O5, vanadium in a square pyramidal environment, has this crystal field splitting, which puts a vanadium 3D XY state at the very bottom of the conduction band. Okay, so this 3D XY state, and this is some X-ray absorption spectroscopy, where we were able to figure out that this is 3D XY state. This is over a decade ago now, and this state splits off from the rest of the conduction band. But this is a problem because essentially it's a very narrow state. So if you think about this as sort of a highway, if you instead of having a highway, you have a very small lane and you have to drive through it, right? It's going to be slow, right? So the electron that localizes in this conduction band has a pretty high mass and has trouble moving through the lattice. right? So this is quite problematic. So now when we started doing these experiments, looking at this material, we understood what the problems were. We've got a substantial challenge both in terms of ionic diffusion, the large changes in coordination number, and then a substantial challenge both also in terms of electron conduction. In my group, we do a lot of X-ray microscopy. It's a fairly sophisticated tool. It's work done at the Canadian Light Source, the Advanced Light Source. And what we do is we can use a very finely focused X-ray beam and just use that to image samples. And this is an example of how you image it. And at each point, we get a spectrum, right? An absorption spectrum taken as a function of energy. And so this gives us the ability to image individual particles as lithiation happens. And so this is an example of an X-ray X-ray absorption spectrum collected using StickSim. And you can see we see very sharp transitions. And we can explain the transitions using basic crystal field theory, right? So you've got the dxy states at the bottom of the band. You've got dxd and dyz states and dz squared dx minus y squared type states, right? And so as lithium ions come in and reduction starts, what happens is just like you would expect from crystal field theory, the dxy states starts getting filled first, then your dxd dyz states, and then finally dz squared dx minus y squared states, right? And so we can calibrate this. And also as this happens, this is the vanadium L3 edge, where we're looking at transitions from vanadium P to vanadium D states. And then at the oxygen K edge, we're looking at transitions from oxygen 1s to oxygen 2p, but the oxygen 2p is hybridized with vanadium 3d, and we can see this crystal field splitting, the T2G and EG star. And what ends up happening as we lithiate, the T2G peaks are becoming weaker, right? And so you can sort of see this a little bit more clearly here. As lithiation happens, these dxy states get filled, and the T2G intensity steadily decreases. Okay. So then, because we've got a very, very finely focused X-ray beam, we can image individual particles, and you can sort of see this here, right? You've got sharp dxy, T2G and EG at the oxygen K edge, and then you take a look. After lithium-ion intercalation happens, this dxy feature has gone down because the vanadium is no longer 5+; it's been reduced, and so these empty dxy states at the bottom edge of the conduction band have been filled. The T2G states are also getting filled, and so the relative ratio of T2G EG star massively changed here, right? And then when we pull the lithium out, okay, we kind of go back to the same thing that we saw before. The dxy state is restored because we've oxidized the vanadium back to V5+, and then again you can see here the T2G EG star ratio has recovered, right? But if we take this middle the lithiated version and we map it, we actually found 3 entirely different signatures, right? This corresponds to a relatively low degree of lithiation. This corresponds to a medium degree of lithiation. This corresponds to a pretty high degree of lithiation, right? So essentially what is going on is that what you're directly measuring is lithium ion concentration and the extent of vanadium reduction. And so we are seeing some pretty large discrepancies even within one particle. You've got different amounts of lithium even inside one particle. And so why is it that the lithium is not freely moving? And this has something to do with the fundamental nature of storing ions in large band gap transition metal oxides. We need to have large band gap transition metal oxides because that's what you get the voltage from. But then the challenge with large band gap metal oxides is that they are typically not very conductive, right? And so what happens here, if you can take a look at this animation, and when an electron comes in, that electron localizes on the vanadium side. And it actually, if you take a look at a charge density difference map, it traces out the contours of a vanadium 3D XY state. So the electron is localizing in a 3D XY state. And because the electron is localizing, it's not spreading out, it's not delocalizing, right? Because the electron is localizing, the lattice actually slightly distorts. and then that distortion of a lattice and its electron is called a polaron. And that polaron binds the lithium ion, and this is called self-trapping. So the polaron, which is the electron plus the lattice distortion, can be a little bit more difficult to move through than a delocalized electron, or a lot more difficult to move. And then the self-trapping of the lithium ion also makes ionic diffusion difficult, right? So essentially, polaron formation is a major problem to the diffusion of lithium ions and electrons in the lattice. Okay, so the added electron localizes in a single ion. So this is important. Again, just to summarize this, we actually end up getting this polaron feature. These narrow, and they're a direct result of this narrow 3D band, which gives rise to strong electron correlation. And upon lithiation, these electrons localize in dxy states. And upon when you combine it with a lattice distortion, you get a polaron, and the polaron is further stabilized by with the lithium ion to essentially give you a self-trap polaron. Let me see if there's an animation here. Let me see if I can play that, but maybe not. Maybe not. Okay, so the message of the story, this is a discharge curve. Okay, the structure, because of these deficiencies that hold up lithium diffusion, means that there's a local buildup of lots of lithium ions because the ions are not moving freely, and that induces these large concentration gradients induce this series of phase transformations. Okay, and these phase transformations therefore then cause all sorts of other problems that I'm about to talk to you about. But fundamentally, what I want you to appreciate is that a lot of these problems are coming and are directly traceable to the basic atomistic chemistry of it. And so all of these concepts that you learn about in your undergraduate classes about crystal field splitting and about electron localization is directly applicable to these macroscopic function of lithium-ion batteries that affects our daily lives, right? And so this is the polaron that you actually see, and this is what's implicated in blocking polaron diffusion. Here's some photo emission spectroscopy we've done, where you can actually see that as the dxy states get filled, the D to D transitions in the field of the filled states are dramatically increasing. Okay, so this is good. Because you cannot, because of this polaron limitation, you end up having this series of phase transformations. And essentially what happens is that as the lithium ion concentration increases to accommodate the lithium ion concentrations, right, these higher, more distorted phases are formed, and you end up inducing these diffusive phase transformations. So this is a phase diagram, and I'm going to show you a video. They're not playing. I can. Okay. Let me try that again. Can you still see it okay? Okay. Yeah. Okay. There we go. All right. So you can see the distortion of the lattice as more and more lithium ions come into the system. Okay. Again, so at a single particle level, because of these polaron limitations, you end up getting these lithiation gradients and phase gradients. And this is the work of Luis de Jesus and Justin Andrews to image this using X-ray microscopy, and typically observed in large particles. And then when we look at networks of particles, we also see incredible amounts of heterogeneity, right? So the red is relatively less lithiated, blue is more lithiated, green is intermediate lithiation. We end up seeing, as you can sort of track here, some very large degrees of inhomogeneities in lithiation across particles. And this is actually quite a substantial problem when folks make these models for how batteries work. A lot of times they use very average sort of coarse grain models that oftentimes do not take into account the very local nature in a complex cathode and of how intercalation reactions happen, often in a particle by particle manner. Okay, and one of the cool things that we were able to image are these phenomenon like you see here of charge striping, right? So stripes being formed within individual particles, right? Oh, so what are the implications of this? So actually, also the charge striping corresponds to lithium and no lithium. So you sort of have these domains, and what ends up happening because of these within individual particles, you get these gradients in lithiation. Now these gradients mean, again, we saw that lithiation causes a change in lattice volume, and so local changes in lattice volume then result in longitudinal and lateral strain. And anytime there's a strain and you have a brittle material on the strain and you cycle it, what happens? Fracture, right? So the particle will end up breaking, and ultimately, as the particle breaks, this is why as your cell phone becomes 1 year old, you get less and less capacity out of it, right? So even though it's telling you that your phone is charged 100%, you're not getting enough capacity because the capacity, more and more of your cathode material is perhaps no longer accessible to do energy storage because it's cracked off, right? So this is some work with Dr. Peter Stein and Professor Baishang Zhu's group in TU Darmstadt looking at these stress inhomogeneities, right? And they're really critical for many things, right? And then we've also looked at these mesoscale heterogeneities across networks of particles. We see very large inhomogeneities. Typically, we see transport being favored across particle boundaries, and lots of secondary nucleation events happen at tips. And here's an example of a little movie. So I'm glad I'm able to play it. You can see that lithiation is induced at tips, and then that the lithium actually transfers between these two wires, and so you end up getting one particle ends up getting lithiated before the other one, right? So you sort of have this sort of particle by particle lithiation that takes place. This is work with Ying Zhao by Shang Zhu's group again at TU Darmstadt. And then when you have curvature here, we can also see some very sharp heterogeneity despite very identical lithiation conditions. The bent wire is strongly, and this is actually published now in Materials Horizons. We see these lithium-rich striations, and we've got sort of high lithiated striations right at the boundary, and we can build from our STIXM measurements these composition maps, and then stress maps. Again, this is work of David Santos and Peter Stein, and that induces these stress maps in here. And we've done a bunch of phase field modeling, or Dr. Baishang Zhu has done a lot of phase field modeling, and you can sort of see the different conditions. And based on this, we can derive, we can understand the mechanisms of what is going on here. So fundamentally, lithium ions, when you intercalate, you have a choice of having a single phase, right, with no phase boundaries, or if the penalty for the phase boundary is not too high, you can introduce a series of phase boundaries, and you can instead have phase separation. So kappa here is a measure of the approximate penalty that you end up paying for that boundary, which has to do with the elastic misfit between the two phases, and we can match the simulations to the experiments and figure out the sort of regime we are in terms of kappa that allows us to see these striations. This is not just restricted to V2O5, but what I showed you here is our work, but this is work that has been done on lithium iron phosphate, for instance, where you also see these striations and with very periodic conditions where you've got, and this depending on the free energy separation between phase pure and phase separated states. So the point of this, though, is to basically say, look, we've got these large stresses, von Mises stresses, for instance, plotted here, even within one particle, because of the complexity of the intercalation reaction and the phase transformations that are accessible, and the interplay of geometry, the separation energy between phase pure and phase separated states, and the elastic misfit at phase boundaries gives rise to some very sharp or substantial stress gradients. And these stress gradients over a period of time will actually be manifested in this. And this is a measurement we've done with Matt Farr's group at Texas A&M, where we see the accumulation in stress of a full cell with cycling because of these electrochemistry mechanics coupling. And this is actually a beautiful image that David Santos has taken showing a bent wire that actually gets cracked, okay, after a couple of cycles. It fractures, again, showing the role of this intercalation-induced phase transformations and phase separations, especially in curved regions and particle curvature regions where you can have an accumulation of stress that results ultimately in plastic deformation. So, and this is a major origin of cathode degradation. So I think, again, the lesson for students, perhaps, it's important to keep in mind that we not only have to worry about chemistry, but we also have to worry about mechanics and the coupling between the two, right? So just to summarize this part, small polaronds are problematic. We've located them, we've identified them as the source of the problem. I think anytime you solve a technological problem, you want to start by figuring out what is the problem really, right? We've seen things like charge striping and along wires, including along curved wires, and this is a result of phase segregation, and it has some pretty large consequences on building up these stress gradients inside the wires that are directly related to failure mechanisms and loss of capacity. Okay, and these coupled ionic electronic barriers profoundly alter phase evolution within individual particles as well as across ensembles of particles, and that stresses develop across individual particles and ensembles of particles because of phase heterogeneities, right? So again, the lesson here about the importance of interdisciplinary research, is relating things like crystal field splitting and the formation of a small polaron, then all the way into the mechanical properties and the capacity loss that we see in real batteries in something like a functional cell phone battery that you might be using, right? So how do we solve these problems? Well, there's two approaches we've tried. This is some work that's cited here, as you can see. One is a geometric approach, where we can essentially play with the geometry of the electrodes to try to address this. The second is a chemical approach where we can play with atomistic structure to address these challenges, right? So essentially, one approach we've done is to play with the idea of continuous curvature to see if we can make electrode where you've got continuous curvature as a means of getting high capacity as well as a very rapid lithiation take place without generating large stress gradients inside the structure, right? So we can form these V2O5 structures, these inverse opals. This is we templated using polystyrene spheres, and then you can see here individual particles, right, give you large hotspots, but you generally end up getting very homogeneous lithiation inside these inverse opal structures, right? So incorporating curvature represents a means of improving rate without sacrificing material stability, since you can essentially, since inhomogeneity leads to elastic strain, as long as you can get this very homogeneous lithiation to take place, you no longer have these hot spots and cold spots, and you can get very homogeneous lithiation. So if you now take a look at the stress map, you can see here in a bent wire or single wires have these large hot spots. That's no longer true for these 3D curvatures. Another way of thinking about it is that the 3D inverse opal templates can breathe in and out of the plane. They can expand in and out of the plane, right? And by expanding in and out of the plane, they can mitigate these polaron-induced phase separations. And therefore, this is a great way to get very fast charge-discharge rates without destroying the battery, without building up these large stresses in the battery. And this is sort of exactly what Abhishek Parija and Cody Chalker have demonstrated. Our patterned inverse opal films show, or colloidal crystal templated films show very accelerated kinetics, and we can get very good cycling out of these structures. Okay, and so the moral of the story: curvatures, geometric properties, geometric texturing of electrodes provides a really easy means of resolving curvature. All right, so this is a little cartoon that Steve Cranford drew for us at Matter. Now, in the last maybe 5 minutes, I want to take more time. Let me talk about mitigating a chemical approach to this, and the idea here is to either use doping or metastable phases with alternative atomic structures to solve this problem. And I think I talked about this in my first lecture. Just like you've got graphite is the most stable form of carbon, but you also have other forms of carbon like diamond and carbon nanotubes and buckyballs that have different atomic configurations of carbon atoms, different modes of connectivity, different extents of hybridization. And these modes of connectivity, these modes of hybridization give you distinctively different atomic structures that can be exploited to realize entirely new function, right? And that's sort of the game I'm going to try to show you, is how do we navigate these rugged energy landscapes to tune material properties? Can you identify not just this most stable well, which is the structure of alpha V2O5 I've been telling you about, but entirely different morphologies, right? And so we use this idea of materials kirigami, where we can make these ternary vanadium oxides, and we can etch out the ions, or topochemically de-intercalate the ions to be more formal, to get metastable frameworks, and then we can use those as cathodes, right? And this is an example of alpha V2O5. This is our conventional structure right here, but we also have other structures that I'm going to spend more, especially some time talking about this tunnel structure. These two are exactly polymorphic to each other, all right? Also, this bucket structure, gamma V2O5, and then here's a new structure, which I don't have an animation for, which is a double-layered lambda V2O5, okay? And so the point is that we can, by going to these other polymorphs, so in alpha V2O5, we had 8 to 3 to 8, and I told you that was a problem. For instance, in this gamma prime V2O5, for instance, we go to 5, 3, 4, 3, 5, or in this case, of the zeta V2O5 through 4, 3, 5, 3, 4. So much smaller changes in coordination environment, in coordination number, so the barriers tend to be much smaller. Okay, so this makes life a whole lot easier, and so this is a major issue from the perspective of electronic structure. I showed you the problem with square pyramids. This DXY is split off, and it's at the bottom of the conduction band by itself. And because it's a narrow 3D band, we get accumulation of electrons here that have a hard time moving through the structure. Over here, we get much more diffuse 3D states that are degenerate, and this allows us to move electrons more easily. And so there's still polarons being formed in these lattices inside zeta V2O5, for instance, but these polarons are much more readily able to diffuse through the lattice. So you can see here, this is the alpha phase. We can reduce the polaron formation barrier in the zeta phase, right? So changing the structure and bonding can greatly change the fundamental mechanisms of ion diffusion by changing the coordination environments and by changing the activation energy barriers. So zeta V2O5, this is how we make it. Again, we can make this from either by starting with copper V2O5 or silver V2O5, and we can take the copper ions out or silver ions out, and we can stabilize this empty structure, and we can grow large single crystals of this. And this is actually some very new work that's just appeared and it's pretty unique because we are able to map the atomic diffusion pathways of ions through this using single crystal diffraction. So this actually gives us a very powerful means of looking at the ion diffusion pathways in this lattice, right? So providing us with experimental direct evidence of the sequence in which these sites are occupied in this lattice. Okay, and you know, in terms of the results, of course, it's great to see that this is a very reversible material. We can get up to 440 milliamp hour per gram in ZW205, making use of polymer electrolyte. That's what makes it stable. Right, and so I think I'm going to stop here. I think I'm almost out of time, right? But I think I want to leave you with this thought that, you know, again, that by going beyond the thermodynamic sink of alpha V2O5, we can really access a lot of different structures. And here's how we, for instance, can go into this gamma prime phase or onto these other sorts of frameworks. So we've got a large set of possibilities that we can access. And this is, again, the work mostly of Justin Andrews and mapping this space along with a few other students. And you can think about this as playing this game of chemical Jenga, right? So you can remove these blocks and you can put in other blocks and really at the atomistic scale redefine diffusion pathways that are adopted by ions, right? So just to conclude my talk, cathode design requires consideration of both atomistic structure as well as electronic structure, as well as an understanding of phase evolution across length scales. And so again, really a need to work together, you know, with experimentalists and theorists and across different disciplines. And the metastable phase space provides opportunities for, you know, preserving composition redox, but then accessing, you know, reworking diffusion pathways. Single crystal electrochemistry, we're very excited about this because really I think it opens up a whole new dimension of materials design, of making new functional materials that are very tailored to the needs of electrochemistry. And then linking, you know, length scales is very important. And with a quote that I just, you know, found today, I read this online from Dr. Whittingham, where he said, you know, in 5 to 10 years, we're poised to have, you know, another twofold increase. So, you know, I talked about how in the last 150 years, we've gone 4x. So if we can go 8x in the next 10 years, that will be quite something, right? So I want to leave you with some parting thoughts. This is clearly that we're going to need, this is a burning need for society. We're going to need a lot of battery technologies to power, you know, both grid level storage, electromobility, our next generation of consumer electronics, home power walls, which will be part of this new grid. But the challenge that we're also facing is some real materials criticality challenges. You know, I mean, cobalt, for instance, as well as lithium, the prices are high. We're having a difficult time getting reliable supplies. This is an example of some of the materials demands. And cobalt in particular has been a very problematic material. Most of it is mined in the Democratic Republic of Congo. There's a lot of issues with child labor there. There's lots of challenges with you know, civil unrest there. So there's some really massive challenges we're having to deal with in terms of materials criticality. And there's lots of good reasons to have a diverse range of technologies, not just lithium ion, but beyond lithium ion. So that's going to be the focus of going beyond lithium ion. It's going to be the focus of my next lecture, which is going to be you know, day after tomorrow. So with that, thank you very much, and I'm happy to answer any questions. Thank you, Dr.
Thank you so much, Professor Sarabjit Banerjee, for very interesting talk. Now I request Dr. Fana Riaz to please ask the queries or the questions on behalf of the participants. Dr. Fana Riaz.
Thank you, Professor Tauqir. It's indeed been a very informative lecture, and there are several questions asked by the audiences. I'll take them up one by one. The first one is, can we use COFs and MOFs for hydrogen storage?
Hydrogen storage. Yeah, I think so. I mean, I think that was perhaps a question for Dr. Mao. I know he was talking about hydrogen storage, perhaps. Yeah, I mean, I think COFs and MOFs certainly have potential there. MOFs, especially for hydrogen storage, I think have been very well studied. There's still some challenges with being able to do it at room temperature and reversibly, but I think there's a lot of promise there.
Probably he meant about the battery perspective from COFs and MOFs. So
I see. Yeah. So MOFs in particular have the challenge with MOFs and COFs for cathode applications is they tend to be very porous structures, so the volumetric density is not high, right? But they tend to be very good solid state electrolytes. So that's something that is very promising. I think there's a lot of promise to the use of MOFs and COFs, where not as redox centers, but as solid state electrolytes. And there's a lot of beautiful work out of MIT and several other groups in both lithium and beyond lithium-ion electrolytes based on MOFs.
The next is, can enzyme electrodes versus intercalated electrodes thermodynamics is favorable for enzyme electrodes? How the two differ in electrochemistry then?
So enzyme electrodes, are you talking about doing electrocatalytic reactions using enzymes perhaps? Or
yeah, exactly.
Yeah. I mean, that's a different form of storage, right? So I think for things like lithium air and such, people are using catalysts, or even for lithium sulfur, people are using all sorts of electrocatalysts as a means of mediating those redox reactions at the electrodes. Those are, I think, definitely viable. As compared to intercalation, there's some major challenges. The challenges for lithium sulfur have been in scaling from the level of coin cells, where you have a relatively thin electrode and you can, almost everything's at the surface and the reactions are easy, to pouch cells, where you actually have to have a lot of bulk diffusion take place. And that's been a very difficult challenge that people have been struggling to solve. And there's similar challenges with lithium, lithium air systems. The overpotentials for these catalysts tend to be high, and you also require relatively high partial pressures of oxygen and such, and then having this reaction to take place in terms of getting bulk diffusion, that tends to be high. So currently, I think there's a lot of promise, and if people can make lithium sulfur work, if they can make lithium air work, those are some very promising high capacity systems, but they've had immense challenges with scalability. So not a whole lot of commercial stuff out there just yet. There's lots of promise, but let's see where that goes.
What could be the effect of 4f orbital if we add rare earth metal for battery storage?
That's a good question. Well, so you want redox. I mean, rare earths can be quite good, and some of the beyond lithium stuff I'm telling you about, talking about, will be interesting. The challenge with, if you're going to do rare earth redox using something like europium or something like that, those voltages are very small, so you're not going to get a huge voltage out of it. And of course, in terms of, I was talking about the challenges with sourcing cobalt, and there's a big push to replace cobalt in lithium, sort of cobalt oxide batteries, and people have been working very hard to minimize cobalt. These criticality challenges are much more exacerbated for rare earths, right? So rare earth can be quite sort of prone to supply chain disruptions and costs and such. So I think really the challenge is to, or what people would love to do, is to move to much more earth abundant metals rather than to rare earth metals.
The next one is related to battery storage. What is the role of electronic structure in the battery storage?
Right. So I would say electronic structure is everything, right? Because fundamentally the reaction is a redox reaction, right? So you have to have, the redox reaction fundamentally depends on electronic structure. What are the states that, a simplistic view is to say, look, vanadium's getting oxidized, or vanadium's getting reduced, or manganese is getting oxidized. But there's these are crystalline solids with a band structure, and it's not pure states that are getting oxidized, pure metals that are getting oxidized. It's these hybrid states. And so understanding how hybridization affects these states, understanding that you tend to have in all of these compounds some covalency. So, for instance, something that is extremely interesting that we've been looking at is the lithium-oxygen interactions in these compounds, which for the most part are ionic but have a covalent contribution to it depending on the nature of the structure. So this is something that is also extremely important. So the polaron that I talked about is a direct consequence of the electronic structure, and the polaron is something that is stabilized because of the peculiar electronic structure of this V2O5 phase. And this is something that I think was not fully appreciated before we looked at it. And then I think once we looked at it and identified the problem, we could think about solving it by moving to alternate structures. And maybe now I'll be able to play the video that didn't play the first time around. Let's go here. Yeah, so you can sort of see that here, right? So this polaron is a direct consequence of the electronic structure that you can see on right, plotted right on top, right? And this is going to be something that is fairly generalizable across all of these large band gap condition metal oxides.
Okay, the next one is, could we use organic, inorganic polymers to get around the structural degradation of vanadium oxide?
Yeah, that's a really good question. So yes, the answer is yes. I mean, the challenge is how do you essentially do this without losing capacity, right? So for every vanadium you replace, or a cathode material you replace with something that is only playing a structural role and perhaps not doing redox, then you're losing capacity. So there's a trade-off between how much capacity do you lose and how much retention do you get. But certainly using hybrid materials is a way of imbuing sort of flexibility, elasticity in the structure, and people are certainly very interested, not just with sort of polymer composites, but also with MXene composites or graphene-based composites, where they're trying to see essentially build in means of addressing these large lattice distortions and volumetric changes and accommodating for those.
Could please explain the experimental pathway of diffuse single crystals of vanadium oxide?
Yeah, sure. So yeah, this is something we're pretty excited about because understanding what is the pathway followed by ions through a lattice is very difficult experimentally. Most times people will simply just do some calculations. The calculations aren't very reliable because there's all kinds of inaccuracies to the calculations resulting from effects of strong electron correlation and such. So people have guessed at the pathways through techniques such as NMR, solid state NMR, or such. But what we've been recently able to do is to take these single crystals, for instance, of Zeta V2O5 and lithiate them, and then take the lithium out, and then we can measure using powerful single crystal diffraction the electron density inside the single crystals, as they are getting lithiated, and this allows us to really see. So it's very different from actually making lithium V2O5 from direct synthesis, where everything settles into its thermodynamic site. We're actually looking at the ions at room temperature as they make their way through the lattice, and we're essentially being able to say, okay, here's where the electron density is showing up, and here's where we can refine full lithium sites. Here's areas of diffuse electron density which correspond to some low partial occupancies that reflect pathways adopted by the ions through the lattice, right? So this allows us to, number one, figure out okay, as a function of extent of lithiation, depth of discharge, what is the order in which sites are occupied? So in this structure, for instance, we end up filling the beta sites first, and then the beta prime sites, and then the C sites, and then ultimately we actually start filling these sites that are outside of the tunnel. So this is a very powerful way of seeing, well, what exactly are the sites that are filled? How is the ions moving through the lattice? And so, we can refine these C and C prime and beta sites, and then we know the diffuse density of the Q sites, so we can start mapping the pathway to this lattice.
The other question again is related to the same experimental pathway. The participant wants to know that, could you please throw more light on the X-ray diffraction of V2O5 to determine the dynamic diffusion pathway, since the single crystal only gives a static picture of molecules?
Right. So we measure the single crystal the same single crystal at different extents of lithiation, right? So this is not particularly fast because we have to acquire single crystal diffraction at different extents of lithiation, but we can get at every point a very detailed pathway. So, okay, and I think I understand where your confusion might be coming from, right? So again, we're lithiating an intact single crystal, right? We're not making a single crystal of lithium V2O5. We're starting with V2O5, we're lithiating it, and we're looking at the electron density maps, and we're saying, well, look, these are the regions where we can refine actual lithium sites, and then here's diffuse regions where there's traces of electron density that we can start mapping. And at room temperature, there's some occupancy of lithium there. It's not a full occupancy, but we can basically say, well, okay, these are the pathways where at room temperature the ions are in the process of moving, right? So this allows us to essentially map this, and you can increase temperature and sort of watch these change. And so even for a single crystal at one temperature, you can start, or at one extent of lithiation as a function of temperature, you can start seeing where the electron density appears, and you can basically say, well, okay, that is the path that is thermally accessible to lithium at a particular temperature.
Okay, the next question is, can we use beryllium ions to design V2O5 framework?
Yes, and we have. It's just beryllium is pretty toxic, right? Difficult to use, difficult to work with. But apart from that, no other reason not to use it if you'd like. Yeah, so the main challenge is toxicity.
Okay, the last question, why energy storage techniques and applications are not commonly practiced for sustainable developments in a country like India, despite enough availability of natural conditions?
Right. So I think, energy storage has had in the midst of a massive boom, lots of stuff going on, and there has to be an investment in battery manufacturing, in battery technology development, and it's a constantly moving field. But India, I think, has invested massively in renewable energy as a whole, in solar particularly, right? So I think the time is now ripe for a similar big investment in battery technologies. And I think one of the advantages of not having done this is that India can learn from the experience of other countries, right? And I think one of the lessons to learn is not to put your eggs in the same basket, to make sure that you have a diverse range of technologies that you can rely on, not just lithium-ion batteries with cobalt cathodes, where you're left struggling to source cobalt from Congo, but a wide range of lithium-ion technologies with different cathodes, like lithium iron phosphate, like vanadium oxides, as well as redox flow batteries, as well as perhaps if any of these alternative technologies like lithium sulfur and such ever become reality. Okay, so I think that would be the lesson to take, is that for renewable energy we're going to need a whole range, and we're going to need manufacturing there across the range. And I want to add one more point, is that one of the things that has happened even in the U.S. For years the U.S. was doing okay, but there's been a massive investment in China and South Korea in battery manufacturing, right? And so the question is, anytime you're looking at the magnitude of the investment, how does a company that is getting started with indigenous manufacturing compete? And so this is, I think, not just about science. It is a lot about science. It's a lot about manufacturing. It's about supply chains, but it's also about economics. It's also about policy incentive. It's also about governmental support, right? So this has been a challenge in the EU, in the US. I think the US and for instance in the UK, a lot of folks are now waking up and saying, oh, okay, we're actually in a pretty bad situation because we don't seem to have a full viable battery manufacturing supply chain in our countries. And this is something that is obviously very troubling because batteries are going to be at the heart of many sorts of storage, many sorts of technologies, and to not have a indigenous manufacturing thing is a major problem. So you're seeing massive investments in Germany, in the UK to revive battery manufacturing. They're not doing it there too, so there's a big push to do it. And I think India will likely have to make those investments as well.
So I guess we are over with the questions, and we've done a very detailed discussion on the significance of developing lithium-ion batteries and the concept of energy storage. And it was a very informative lecture, very detailed discussion along with the statistics and the challenges that we could face in future. And I can see that the participants have really been engrossed with all the data that you've shared, and they've posed very significant questions, relevant questions, which shows that they've really enjoyed your lecture. And every day, it's like going into a new dimension of research. It's very exciting, and the lecture series is getting, very interesting day by day. And we really thank you for your efforts, Professor Banerjee. You've been really helpful to share such wonderful information with the participants. I thank you for being with us, and we'll hope to see you again day after tomorrow, I guess. So
day after tomorrow. I'm looking forward. Thank you, Dr. Riaz, and I'm looking forward to talking about some more frontier stuff that is still sort of further out there and beyond lithium technologies. Thank you again.
Okay, thank you. Thank you for the wonderful lecture. And I would like to hand it over to Professor Tauqir for the formal closure of this session.
Thank you so much, Dr. Fana Riaz. Thank you, Dr. Fana, for taking almost all the questions very honestly. And I express my sincere thanks to Professor Banerjee for actually entertaining all the questions and give the very, very, very satisfactory response. And we are looking over the compliments that we are receiving from the participants. They are extremely happy with your lecture. Thank you so much for very, very interesting talk. Thank you, sir.
Thank you so much again, and look forward to seeing you in a couple of days. Thank you. Bye.